Hi everyone, good morning. My name is Dr. Smita Ghosh, and I am an assistant professor in the Department of Mathematics and Computer Science at Santa Clara University. And I will be presenting our paper today, which is titled A Data-Driven Strategy for Online Hate Speech Spreader Identification Using Modified PageRank. And along with me, I have Shiv Jhalani, who's worked on this paper, who's also a student in the same department. So to introduce our problem that we worked on in this paper, in the past decade, the popularity of online social networks has significantly increased due to the widespread availability of the internet and the affordability of electronic devices. This surge in users has led to a substantial growth in content consumption and the amount of time individuals spend on these platforms. In recent years, hate speech has emerged as a growing criminal issue, not only in face to face interactions, but also in online communication. There are several contributing factors to this concerning trend. Firstly, the internet, particularly social networks, provides an environment where individuals are more prone to adopting aggressive behavior due to the shield of anonymity. Secondly, people are increasingly inclined to express their opinions openly on online platforms, inadvertently fueling the propagation of hate speech. Given the immense harm that such prejudiced communication can inflict on society, both governments and social network platforms stand to benefit from the development and implementation of detection and prevention tools to be able to identify these kind of users who can be flagged as potential threat to the network. So in this paper, we have proposed a modified PageRank algorithm called the hate speech potential rank, which is proposed and uses a data-driven metric called hate speech potential to generate ranking of users on an online social network. As you can see on the screen here, we have a social network where users are connected to each other. What our algorithm intends to do is for each of these users, it intends to provide a rank or a label such that we can flag those users in a large network. Like, for example, here we see that most of them have ranks like 0.16 and 0.27 and 0.34, but there are these two users who tend to have a rank much higher than, let's say, the 0.5 threshold. So they have a rank of 0.81 and 0.91. So our goal is to be able to generate these ranks such that given a threshold, we can flag certain users as being potentially harmful or a threat to our network, while the others can be just considered as non-threatening. So this is what we have proposed in our paper, where we want to utilize this modified PageRank algorithm, and we want to be able to identify the pool of potential sources and spreaders, which initially consists of billions of users, and somehow be able to come up with a small collection of those users. And then the task of the online social network provider would be to monitor and control the dissemination of hate speech by flagging those particular users. So the main contributions of this paper were threefold. The first one was we introduced a data-driven metric called hate speech potential. The second one is using that data-driven metric to identify spreaders of hate speech on an online social network. And the way we did that is we utilized the traditional PageRank algorithm and we modified that, and we called it the hate speech potential rank algorithm to provide the hate speech potential rank of each users that will help us to differentiate a threatening node from a non-threatening node. Another important aspect of this paper is the concept of PageRank algorithm. So the PageRank algorithm is a very popular algorithm employed by Google search to determine the ranking of web pages within their search engine results. The way it works is it operates by assigning a numerical value to each web page, and this numerical value actually has an importance. It's known as the PageRank score, and that rank actually conveys the importance of how good that web page is in terms of quantity and quality of links that point to that page. So this motivated us to try and draw a similarity between PageRank and spreader detection. So what we tried to do was, where just similarly how a PageRank algorithm assigns higher importance to websites with more inbound links, where a web page which is connected to a more important page tends to have a higher rank, and more number of web pages they are connected to will also contribute towards a higher rank. So similar approach can be employed to identify users who disseminate hate speech through connections in the network. So the first thing that we had to do was to convert the web graph of web pages into a social network. So we drew the similarity there, where in a web graph, each node was a web page, but in our scenario, each node became a user on the social network. And in a web graph where the connections were represented as hyperlinks, for us, the connections could be followers, friends, or it could be a message passing connection, and any type of connection that would connect two users on a social network platform. So the idea here was, if a user A is connected to multiple users who have a tendency to spread a lot of hate speech, then their potential to spread hate speech also should increase as they are exposed to more hate speech content. What do I mean by that? Let's just try to visualize the scenario. So given a page rank, so the graph that you see on the left is that of a web graph. So each of those nodes is a web page, and then the connections between them is a directed edge, where if a hyperlink exists from one page to another page, that is depicted using a directed arrow. So as you can see, web page A tends to have the highest rank because it is connected to a large number of web pages, each of which have a very high rank or importance themselves. So something similar can be observed in a social network as well. So let's imagine that Alice, Bob, and Chris are connected on a social network platform such that Bob follows both Alice and Chris follows Alice. So in this situation, let's say Alice and Chris both have a very high tendency of spreading hate speech, either individually or being connected to other people. But for this scenario, let's assume that Alice and Chris both have a very high tendency to post hate speech tweets themselves. So Bob, being a user who follows both Alice and Chris, should also be categorized as someone who has the potential to spread a lot of hate speech because they are connected to Alice and Chris, who individually tend to have tend to have the tendency to spread a lot of hate speech. So in this case, if Alice and Chris tend to have a high potential to spread hate speech and Bob follows both of them, then Bob's spread potential should also increase, which is the similar concept in a PageRank algorithm. So this kind of motivated us to draw the similarity between the PageRank and the hate speech spreader detection problem. So for implementing the experiments in this paper, we chose Twitter as the social media platform. Now, there were multiple reasons to actually do so. New data suggests that the hate speech is on the rise on Twitter, and Twitter is also a widely used platform with a large user base. The public nature of Twitter allows for easier access to user-generated content, making it relatively straightforward to observe and monitor conversations and interactions. And also, Twitter's network structure is what we were really looking for, is to come up with this directed graph of a follower-followee relationship such that it gives rise to a directed graph instead of just an undirected graph, so that we can implement the PageRank algorithm or the modified PageRank algorithm efficiently. And another feature is Twitter's real-time nature that facilitates the timely detection and response to hate speech incidents, enabling prompt intervention and mitigation strategies. So all of these reasons combined motivated us to use Twitter as our graph data so that we can implement our modified PageRank algorithm. Now coming to the proposed data structure, the proposed model of our paper. This proposed model was divided into three phases. The first phase was what focused on the identification of a reliable and robust hate speech classifier, because whenever a user posts a certain tweet or posts some certain text, our first step is to be able to recognize whether that is hate speech or not. Because the fact that a user by themselves is posting something which is hate speech becomes important. And in reality, these tweets are not labeled. So first and foremost, we need to be able to identify a uh, reliable and robust classifier that can effectively and accurately categorize a post as hate speech. And once we have done that, then phase two concentrates on predicting the labels uh, that we get from phase one. And using those predicted labels, we calculate something called an initial rank HSP, where HSP stands for hate speech potential for each user within the social network. What this does is it gives us the initial rank of the individual characteristic of a user of their potential of posting something which is hate speech related. So if I am a user and I have these 10 posts that I have posted, these 10 posts are going to be fed into the classifier that comes from phase one, where each of those 10 posts are going to be labeled as hate speech or not. And based on that label, I'm going to come up with an HSP value for me, which is going to be the ratio of the number of hate speech posts that I've made over the total number of posts that I have made. And after these HSP values have been generated for each user, together all of those is going to be fed into our hate speech potential rank algorithm, which is going to be our phase three. So let's look at each of these phases as we go. So the first phase is the hate speech classifier, where the entire intention of this phase is to be able to label the posts of each user. Because tomorrow when a new user comes into the network and the posts that they're going to make, all of those posts are going to be unlabeled. So we need this very reliable classifier that helps us to predict the label of that unlabeled post. So we experimented with various text classification models. What stood out for us was this pre-trained model called Hate Sonar, which is a pre-trained hate speech detection classifier. And that gave us the best results for coming up with the labels for the unlabeled posts. So we decided to work with Hate Sonar as our model for phase one. Another challenge that we faced while working in phase one was that the uh, due to the Twitter's API policy and restrictions, we weren't able to actually get the data that we desired within the time frame that we were working on this project. So we decided to focus on a different strategy for coming up with the tweet list for each user. So we came up with this idea where we already had this data set containing hate speech posts that were already labeled. So we decided to just come up with a strategy where we would pick up all of these tweets and then randomly generate a number and pick that many tweets from our data set and then assign it to each of the users. So as you can see in the figure here, we took the entire collection of tweets, which was both hate speech as well as not hate speech. And then we utilized a random number generator to come up with a random number, and that many number of tweets were assigned to each user on my platform. So this helped me to come up with the different tweets that each user has made in a social network, which was utilized. This information was utilized in phase two to come up with the HSP rank or initial rank of each of the users. So phase two focused on the results obtained from phase one to come up with something called the hate speech potential of each user. So for a user U, the HSP value of that particular user is given by this formula, where it is the number of hate speech posts that the person has made divided by the total number of posts that the person has made. So for this, we utilized the classifier in phase one to actually get the labels of the posts, because that would contribute to the numerator, or the count of the number of posts of the numerator would be generated by the labels that we obtained from phase one. And the second part, the denominator, was obtained from how when we built the network, where we built the list of tweets generated for each of the users from the data set that we had. Together, combining these two values from phase one was fed into phase two, which gave us the HSP values of each of the users. So this was where we determined the ratio of the number of hate speech posts to the total number of posts made by the user. So the output of this phase was that now in a network of, let's say, n users, every user has an initial rank, which is based on the individual posts that they have made in the network. So traditionally, the initial ranks of a PageRank algorithm comes from uh, either a uniform distribution or some other formula for an initial rank. In our proposed model, what we've done is we have modified that PageRank where now our initial values come from phase 2, where the initial values are the HSP values of each of the users. And because the way the PageRank algorithm works, we needed a normalized value. So phase 3 focused on implementing the modified PageRank algorithm, and compared to the traditional PageRank, here our initial ranks were the normalized HSP values from phase 2. The output was the final ranks of each users that was calculated based on the hate speech potential rank algorithm, and we labeled that as the hate speech potential rank, or HSP. So once we obtained the HSP, we realized that HSP were values that were generated by an algorithm, and it lied between 0 and 1. So at this point, after we have the output from phase 3, we have all the ranks for every user. But now, going back to our initial discussion of coming up with a threshold to determine whether a user is threatening or not threatening, we had to strategize different thresholds to actually flag the users. So we tried to come up with certain strategies. The first one was to have a fixed threshold like 0.5. So if the user had a rank of above 0.5, they were considered as a threat, and um, if they had an HSPR value below 0.5, then they were considered as safe. But based on our experiments, what we realized was that because of the variation of the values, the fixed threshold was not really a good choice because most of our users were either below the threshold or above the threshold. So that's when we decided to come up with two different strategies. One is the average sum. So we took all the HSPR values of all the nodes that we got from the algorithm in phase 3, and we averaged it out and used that as a threshold. And the other one was we took the maximum and the minimum value of the HSPR values that we had obtained from phase 3, and then found the average of that and used that as a threshold. So these were our data-driven strategies to come up with the threshold to kind of differentiate between a threatening and a non-threatening node. And to evaluate this, we actually experimented with 3 graphs and implemented the K-means algorithm as an evaluation measure to evaluate our proposed strategies. So we experimented with 3 graphs. Graph 1 and graph 2 were small graphs that were randomly generated. Graph 3 was the Twitter graph that we built based on the discussions that we did when we were building the tweet list for each user. So graph 3 is a Twitter graph, and graph 1 and 2 are these small randomly generated graphs which we experimented with. So to assess the effectiveness of our approach in identifying the hate speech spreaders, we employed the K-means clustering as an evaluation measure. So if you look at the table here, you'll see that the two strategies that we determined, one was the two strategies that we proposed, one was the average sum and the other was the average max min. So when we experimented with these strategies, we noticed that for average sum, the number of spreaders were 2, 8, and 189 for the 3 graphs, and the number of spreaders for average max and min were 3, 6, and 134 for each of the graphs. And when we utilized those HSPR values and utilized it with our K-means algorithm, we got very similar results. As you can see here, K-means algorithm said for graph 1 there were 2 spreaders, for graph 2 there were 9, and for graph 3 there were 183. So this helped us understand that our proposed approach was actually effective because the K-means algorithm, which is an unsupervised machine learning algorithm, helped us to evaluate our strategies and gave very similar results that our proposed strategies also tend to give. So to conclude, we can say that we designed a modified PageRank algorithm to help find spreaders of hate speech on a social network. And the experimental result shows the effectiveness of the proposed approach. But our work does not stop here because throughout the entire experimentation, we realized that there were a lot of challenges that we faced. And so that helped us to understand the future directions of this project. Like one of the most important things that we realized was we had to constantly improve the proposed algorithm's accuracy, scalability, because we only worked with 3 graphs and 2 of which were very small in nature. So we would want to kind of experiment with larger graphs as well to see how well our strategies perform there. The second one was, of course, we only used the fact that a user was making a hate speech and then using that as the starting point to come up with ranks and the network structure, which gave us the implementation of the modified PageRank algorithm. But one thing that was lacking in this work was incorporating any user profile information such as demographics, past behavior, and other different social network features, which can provide valuable insights into the motivations and patterns of hate speech spreaders. So this is something that we have not experimented with yet, but definitely is on our to-do list in order to keep working on this project. And another is that we did not really consider the context aware analysis of the situation, where we did not include any temporal dynamics and regional variations, which can provide a more deeper understanding of hate speech propagation across these different platforms and communities. So all of this is definitely something that we did note down because we would want to keep working on this in order to make our algorithm and proposed strategies more effective. So this brings us to the end of our presentation, and here's the and here's where I would have asked if you had any questions for me, but because unfortunately due to time difference I couldn't be there. So I would just like to end this presentation by first acknowledging the support that we have gotten from the Department of Mathematics and Computer Science at Santa Clara University, and also some student workers who helped us to run some of the experiments, especially a student named CJ Oshiro, and he was responsible for some of the experimentation in the paper, along with Shiv Jhalani, who was the main contributor of the implementation in this paper, and the entire Department of Mathematics and Computer Science for their support throughout this project. And then finally, I would like to thank all of you, all the organizers of the conference, and also people attending. Thank you so much for your attention and for being and giving me this opportunity to present our paper. If you have any questions, please feel free to send me an email. My email is sghosh3@scu.edu, which should also be on my paper. So please, if you have any questions, any follow-up questions, please send me an email. But thank you so much for listening to my presentation, and hopefully you have a great rest of the day. Thank you so much for um, being here, and thank you so much for this opportunity. Thank you so much, and hope you have a great day. Thank you.